Hi, Math 105 student. This is a brief video to review some of the fundamental ideas about quadratic functions, as well as the process of completing the square to change the form of the quadratic from standard into vertex form. So a few things going on here, but let's review some of the basics and some of the ideas so that you have cohesive understanding and can make sense of all this stuff about quadratics. So the first thing is that the definition of the quadratic function. Any function that can be written like this, ax squared plus bx plus c, is what we classify as a quadratic function. The b and the c could be 0, leaving us with just ax squared, and that's the most basic quadratic function. But the a cannot be 0 because we must have the x squared term so that it is a quadratic function. Does it make sense? And in addition to that, the a, b, and c, just a side note, are just the coefficients. So if we ask you what a, b, and c are, they are just the coefficients. For example, if I write, see, 2x squared minus 3x plus 4, that's a quadratic equation where a would equal 2, b would equal -3, c would equal 4. Okay? So the graphs of every quadratic function, all the graphs are going to be parabolas. And the reason for that is that that key term, that first term that must be in every quadratic function, has this kind of bounce characteristic about it. Let's take a look at the most basic of the quadratics, x squared, to see what I'm talking about there. So if we look at x squared, and we think about some of the points that x squared has on it, let's say x and x squared. We know, first of all, that if I square 0, I get 0. And that happens to, by the way, be the vertex. But here's why it's the vertex. If I take -1 and square it, we know that -1 times -1 is +1. So moving left 1, I go up 1. However, we also know that if I take +1 and square it, I get a +1. And so right around that vertex, we have this bouncing effect. The function does the same thing to those inputs left of the vertex that it does to the inputs same distance away to the right of the vertex. That's why we get this parabola. Same thing. So if I put -2 in, I'll get +4. -2, +4. If I put +2, I get +4. So that's why this bounce happens. And also, while we're there, every quadratic has this line of symmetry, or axis of symmetry, if you will. It cuts the parabola in half right through the vertex. It makes it easy to graph other points, because if you know some points on the left, you can get some points on the right. Okay? And that axis of symmetry always goes right through the vertex, because the vertex is at the bottom, so it's, it's at that midpoint, kind of that bouncy point that cuts the parabola in half. The axis of symmetry, by the way, always is a line, and so we get it, we write the equation as a line, as x equals something. In this case, the line of symmetry would be x equals 0. And we see that x is 0. It never changes its value. All of the x's on that line are 0. Y changes its value. It goes up and down, but the x never changes its value. So that's why that equation is x equals 0. Okay? The axis of symmetry over here on this parabola to the right would be, yep, got it, x equals 2. And we do give the equation of the axis of symmetry. The full equation, because it's a line. It's a line. It has more than one point, so we don't just put 2 down we say x equals 2. Y can vary, but x is stuck at 2. All right, hopefully that explains the nature of these quadratic functions. So now we turn to the forms of them. We have 3 different forms. We have the standard form, the factored form, and the vertex form. And just like how you represent yourself differently depending on the context, these forms, they give us different information. They're just different representations for the same exact thing. So if we write the quadratic function in standard form, we can see one thing, that if we put 0 in for x, the output f of 0 is just going to be c. We'll get a times 0 squared plus b times 0 equals c. So we know that 0, being the input, has an output of c, and so the standard form would always provide us with the y-intercept. It's nice. Just look at it and know that. But it's nice to know why, not just memorize that c is the y-intercept. To know that if we put 0 in for x, we're going to get c. In the second form, and so if I'll just put it there. And we can see 0, c. The second one is the factored form. And if I look at factored form, I have a times x minus r times x minus s. Look at this. If I let x be r, that other thing, to zero out that factor, if I put a value in for x, whatever value I put in for x that zeroes that factor out, it's going to make the entire function equal 0, because you know that 0, if I have r minus r times r minus s times a, that's going to be 0. And 0 times anything is going to give me 0. So I can say here that g of r equals 0. If I put r in for x, out comes 0. So that's why this form gives us the x-intercepts. By the way, same reasoning if I put s in. So I'm just going to write r over there, maybe s over here. You can see that those are r0 and s0. And the y-intercept is 0, c. And the last form, by the way, I did mean to mention that not all quadratics are factorable. So yeah, there are some you cannot find those x-intercepts by factoring. And maybe a quadratic doesn't even have any x-intercepts, by the way. We'll save that story for another day. But if the parabola looks like this, there are no real x-intercepts. Okay? The vertex form looks like this, and this is due to the fact that it's a shifting, more or less, of the parabola. Again, if you think about letting h, or excuse me, letting x be h, whatever zeroes that portion out, that's going to be the bottom of your parabola, just like it was in the previous page, that bottom portion, okay? Because the parabola is going to be symmetric about either around that bottom vertex point. So if h is put in for x, I'm going to get 0, and that's the smallest value that something squared could be, right? That's why it's a vertex. Smallest value could be, you can't square something in a negative, so if we put h in for x, that's going to make that value the smallest. So h will be where the vertex occurs. So horizontally, we shift the parabola left or right, and then adding k to all of those outputs moves the parabola up. So it might be, or down, I guess. So if I move it to the right, H, and then up K. And that's why the vertex is at HK. Again, if you have something like this, x plus 3 squared minus 5, what value for x would make that inside 0? Answer, -3. So that's going to be your lowest point. Everything to the left and right of -3 square out to be the same thing. And then the parabola is shifted down 5 units, so -5. So there's your vertex for that. H would be -3, K would be -5. So my vertex is HK. Okay, so each one of these forms gives us some different information about the quadratic, or excuse me, about the graph of the quadratic function or the parabola. So it's nice to also be able to move between the forms, right? You've already moved from standard form to factored form by factoring. That's why we're practicing the whole thing about factoring. Going from standard to factored form, we factor. If we wanted to go from factored form to standard form, we'd simply expand. We multiply out those factors. So that's an easy process. If we wanted to go from vertex form to standard form, from vertex form to standard form, we would expand. We could just multiply that whole thing out. We'd multiply this out and subtract 5, and voila, we'd get it in standard form. If we wanted to go from standard form to vertex form, it's a little more complicated to go from standard to vertex form. We do what's called completing the square, and I'm going to run through that right now. So this is just the way to convert all of these forms to the other. So, oh, and additionally, I wanted to mention that, you know, it's really important to think graphically because it will drive some of your answers for some of the questions. For example, if you're asked, oopsies, about the axis of symmetry, the axis of symmetry, you should know, goes right through the vertex. So if your vertex was down here at point AB, you would know that the axis of symmetry has the x coordinate, never varies, and it would have the equation x equals a. All right, so think visually. Just think about that axis of symmetry and where it would be on the parabola. Goes right through the vertex. X never changes, so x equals that x coordinate of the vertex. Second thing, the minimum is always the lowest value. Okay, so it would be the y coordinate of the vertex. Since y's go up and down, we look at the y value for our minimum. So here, that minimum would be b. And there is no maximum. Infinity is not a maximum. There is no maximum here because that curve would continue to go up and up and up and up and up to infinity and beyond. So we don't call a maximum there. So a curve only has one min or one max. A parabola only has one min or one max, not both. So let us review how to complete the square on this particular quadratic function, which is written in standard form. Since it's in standard form, we can see that if x was 0, we'd get out 24, and that is the y-intercept. All right. So now we're going to try to put this in vertex form, showing each step. All right, I'm going to use this particular template that I have that my students received in their classes. So the first step in writing this lovely thing in vertex form, this first step is to factor out that a value only from the first two terms, which is kind of odd because we're so used to factoring a GCF out of the whole thing, but now not with completing the square. We only factor that a term out of the first two terms. Notice you have to be thinking about distributing a -3 to x squared and a -3 to a -2. And then we leave 24 there. Okay, so this phrase is still equal to r of t. It's exactly r of t. Haven't changed anything, just brought the -3 out of the first two terms. The next thing we do is complete the square on the inside terms. So we have this part of a trinomial square on the inside. Now, this is still equivalent to r of t, but I have to figure out what do I put in this blank so that when I square a binomial, that is my trinomial square. So I'll write that over here. Something squared, blah, 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 is equal to x squared minus 2x plus blank. Okay? And here's how you can manage that. In order to figure out that, you take half of b. B here would be -2. So half is -1. We square it. We get 1. We add it inside. Since we square it and add it, it's always going to be positive, so we know that that's +1. Okay? All right. Now, one thing is that I just changed what r of t is equal by adding this 1 on the inside, so I'm going to have to do something on the outside to compensate for that. Okay? So thus far, I have -3x squared minus 2x plus 1. That's a trinomial square. Plus 24 from the original, and then I have to figure out what I need to compensate. So I didn't just add 1 here. If you look really carefully, there's a -3 outside. So I actually added -3 to the expression. So in order to compensate adding a -3, I have to add 3 to keep it balanced. Now they're equal. So I have -3 times x squared minus 2x plus 1 plus 27. That's still equivalent. So now I factor the perfect square trinomial. This is where your factoring skills come into play. What is x squared minus 2x plus 1? So we know that the design is to get this perfect square trinomial, but if you remember, you can think about first, outer, inner, or last if you really want to do that. If you don't see it as a trinomial, because x times x and what times 1, 1 times 1 is, gives you that 1 over there, and -1 and -1, so it's x minus 1 squared plus 27. And that is my vertex form. Okay? There's a few steps, but you know that this has to, if it is correct, if it is the correct vertex form, it has to be equivalent to the original standard form. It has to be equal. It's just written a little differently in a form that gives us information about the vertex. Okay? So How do we check if we've completed the square correctly? Well, we can multiply out my vertex form to see if we get the standard form. So I'm going to do that real fast. I'm going to say -3 times, and I'll write this out so I don't make any mistakes. If you don't know the pattern for squaring a binomial, this is the way you do it. So now I say x squared minus 1x minus 1x for that inner term, and then plus 1 and plus 27. And that, of course, gives me, for that inside, x squared minus 2x plus 1. Again, that pattern is double the product, right? This squared, the first term squared, double the product of the inner and the out, first and last, and then add the last squared. Then, after I multiply that out, I distribute the -3. Negative times negative, positive, plus 27. And I combine anything. -3 and positive 27 give me positive 24. And then I look over there and I go, yep, yay. Alternatively, if you don't have to show any algebra or you have decimals nearby, you could graph both of them and see if they are the same. Let's see. Whoops. So if you look in the red graph is the standard form here, and the blue graph is the completed the square, the vertex form that I got. And we see that they lie right on top of one another. Turn off the blue, they are identical. Other ways to check too, but I'll leave it at that. Going back. All right, so then if we graph f, let's see if I can remember, we had, I'm going to have to go back, we had 127 here would be my vertex. So I'm going to say 1, and I'm going to scale these by tens, 10, 20, 30, and so 127 is going to be probably right about 225 and 30, so right about there. Label it 127. It's 30, 20, 10, and there's 1. So there's my vertex. My roots, I'm going back a few pages. Oh, I didn't find my roots. Did I? I need to find my roots. I've done part C. I've done part B. The vertex we got was 127. By the way, H is 1 and K is 27. They are the coordinates of the vertex, always. The axis of symmetry, if you think about the parabola going through that vertex, 127, and since A, I believe, is -3, so I have a downturning parabola, and that axis of symmetry goes right through 127. So it has an equation of x equals 1. And since that A is negative, we do have a max. Its value is 27. And how do we find the x-intercepts? So we take that lovely equation negative 3x squared plus 6x plus 24, and we factor it. So this is a different process than completing the square. We do our normal factoring and we take the entire, or excuse me, take the GCF out of the entire thing. So I'm going to take negative 3 out of every term now, because factoring I want to rewrite as the product. So I take negative 3 out of x squared, I get negative 3x squared. Take 3 out of 6, I get negative 2x. Take negative 3 out of positive 24, and I get negative 8. And this trinomial looks like it can be factored as x and x, and minus 4 and plus 2. You can check that, but negative 4x and positive 2x give me that negative 2x in the middle. So it looks like my x-intercepts would be 4, 0, and negative 2, 0. So I'll go back to my graph, 4, 0, and negative 2, 0. 4, 0, and negative 2, 0. And that's perfect because vertex is right in between. Halfway in between. And I grab this up. Oh, maybe I should look at what my y-intercept was. What was my y-intercept? Did I find it? Yes, 0, 24. So right about there, just under 25. And I'll label it 24. Okay, so that's my complete graph. If you had this on a normal scale from the vertex, we might note that since that leading term was negative 3x squared, instead of going 1 over and 1 down, we'd go 1 over and 3 units down. Which makes sense because if I go from 127, 1 unit over, 3 units down will be 24. It's kind of hard to see in this weird scale, but instead of 1 over 1 down, I'd go 1 over 3 down because of that stretch of 3. So just looking at this graph right here, suppose you didn't do all that other work before, you should be able to see that since it's downturning, we know that A would be negative or less than 0. We would see that HK is our vertex, and we would know that H must be there, and that's in the positive x's. So I would say H is positive. And K is up there, which is in the positive y's. So K is positive. R is over here, the lesser of the two roots, and that is negative or less than 0. And S is over here, and that is positive, so greater than 0. And I would see that C is right about there on my weird graph here, and that is positive. Just by looking at the graph, we should know what all of those variables mean. Now it is your job to complete number 2 on this worksheet. And here is a given example, 2x squared minus 4x minus 30, given to you, again, in standard form, very much like the first example. And you would first start by taking out the 2 from the first 2 terms only. Good luck with this. I hope this helped.